Here we have another example of a proof by contraposition. If x and y are integers, such that x plus y is even, then either x and y are both even or both odd. So as usual, your first step should be to write it in symbols. So put your video on hold and write it out in symbols. Here it is in symbols. When we say if x and y are integers such that something happens, the implication is that this is supposed to work for all x's and y's. So it's universally quantified, even if you don't see the words explicitly written here. You have to include them when you write it in symbols. For all integers x and y, if x plus y is even, then either x is even and y is even, or x is odd and y is odd. Now if you were to go ahead and give a direct proof of that, then you would say let x and y be integers, suppose x plus y is even, and then you'd write x plus y as 2k for some integer k, and then you'd be expected to make a statement about each of x and y separately. So making a statement about a sum doesn't really tell you much about the individual parts of that sum, and so that's probably not a good way to do it. If, on the other hand, we decided to do it using proof by contraposition, we'd start with an x and y in Z, and we would say, suppose this doesn't happen. So to say that it's not the case that either x and y are both even or both odd is to say that one of them must be even and one of them must be odd. And because of the symmetry in the expression that you're trying to say something about, it doesn't really matter which one is even and which one is odd. And so we could say, okay, suppose x is even and y is odd. And now you have to make a statement about x plus y, right? If you're doing contraposition, you'd have to try to deduce that x plus y is odd. And if we know something about each of x and y separately, then it's really quite simple to deduce that x plus y is odd. So this seems like a good way to do it. So I'm going to leave it to you. Write up some calculations that suggest the structure of the proof or what needs to be done, and then write up a formal proof, and when you come back we can compare our solutions. Okay, here's my proof. Let me begin by showing you the calculations I did in order to produce that proof. So what we did was we started with an x, which we were able to argue can be assumed to be even, and a y which we can assume to be odd, and then we wrote it in using the definitions. Then we calculated x plus y, we got this, and then we just observed that that's 2 times k plus l plus 1, and then since this is an integer, then that shows that x plus y is an odd integer, and so that's the idea of the proof. And so let's now see how I actually wrote all of this up. Okay, so looking here, I always look at the symbols when I write the proof. This told me I should write let x and y be integers. Now I warn you that I'm about to use a proof by contraposition, so that means that the I next goes here, and we write down the negation of that. We suppose the negation of that is true. Suppose it is not the case that either both x and y are even or both x and y are odd. Well, then you explain what that means. That would mean, or then, one of them must be even and one of them odd. Now I have to argue that it doesn't really matter which of the two is even and which is odd. So I say, since the expression x plus y is unchanged upon interchanging x and y, we may assume without loss of generality that x is even and y is odd. Now I say what the definition of that would mean. Thus there exist integers r and s such that x is 2r and y is 2s plus 1. So notice that you must use different names here and here. If you call this 2r and this 2r plus 1, then you're essentially assuming that y is equal to x plus 1. And if that's the case, then you're certainly not proving anything about all pairs of integers x and y independent of each other. Okay, so you must have different names here and here. And then basically I'm just sort of giving the flavor of what I did. I'm putting everything that needs to be said, but I'm doing it with as few words as I can think to use. I say, thus, adding and collecting terms, we get that x plus y is equal to this, which is equal to this. Since r plus s is an integer, it follows by definition that x plus y is odd. This completes the proof. I just want to point out one thing. The reason that I'm reading this for you is that I want to convince you that the final version of the proof is really an English paragraph. Even though you see lots of symbols in it, we can still interpret everything that I've written as a paragraph. I'm not just simply putting symbols down on the page and expecting the reader to figure out what it all means.